Imagine a future where hopping between galaxies is as common as international flights today. Sounds like science fiction, right? But as the human race looks towards a future beyond Earth, such dreams may become a necessity. In this video, we'll dive deep into the realms of advanced space travel technologies, from the controversial EM drive to the fascinating concept of warp drives. Join us on a journey that stretches not just across the cosmos, but also through the very fabric of physics as we know it. Our planet has been a nurturing home for millennia, but it won't last forever. Whether due to natural disasters, dwindling resources, or simply our inherent urge to explore, the human race must look to the stars for our future. But there's a catch. Space is unimaginably vast. Outer space is so vast it stretches the limits of human imagination. The observable universe, the part of the cosmos we can see and measure, spans about 93 billion light-years in diameter. To put this into perspective, a light-year is the distance light travels in a year, approximately 5.88 trillion miles. Our own galaxy, the Milky Way, is about 100,000 light-years across, containing billions of stars, and it's just one of potentially 2 trillion galaxies in the observable universe. Beyond this observable limit, the universe might extend infinitely. Each star potentially hosts its own system of planets, creating a cosmic landscape of unimaginable scale and diversity. This immensity makes interstellar travel a daunting concept, with distances so vast that traveling even to the nearest stars requires speeds and technologies far beyond our current capabilities. The sheer size of outer space highlights not only the incredible vastness of the universe, but also the relative smallness of our place within it. Conventional space travel, like what got us to the moon, won't suffice for such distances. We need to think bigger, faster, and more radically. The concept of traveling faster than light, a staple of science fiction, suddenly becomes a serious consideration. It's not just about reaching new worlds, it's about ensuring the survival and continuation of humanity. Enter the EM drive, a device that defies the laws of physics as we know them. At its core, the EM drive is an enigma. In simple terms, the drive uses electromagnetic waves, aka microwaves, in a closed, conical cavity. These microwaves are generated using electricity, which can be sourced from solar panels or any other power supply. The microwaves bounce back and forth within the cavity, and the unique shape of the drive is theorized to cause these waves to exert more force on one end of the cavity than the other, creating a net thrust. This design, which doesn't rely on any external propellant, challenges our current understanding of Newton's third law of motion, the principle that for every action there is an equal and opposite reaction. In the case of the EM drive, there's no clear reaction or exhaust, yet it supposedly produces thrust. There's no visible action, just the promise of reaction. Since its inception in 2001, the EM drive has been a subject of fierce debate. Some tests claim to have observed thrust, albeit minuscule, while others dismiss these claims, citing experimental errors or the impossibility of the concept. If the EM drive works, it could revolutionize our understanding of physics, paving the way for propulsion systems that could take us to other stars. But skepticism remains high. Is the EM drive a groundbreaking invention, or will it be remembered as a scientific misadventure? Let's step back to our current reality. Today's space missions rely largely on chemical rockets, which are powerful but inefficient for long-distance space travel. They require enormous amounts of fuel and offer limited speeds. An alternative that's been gaining traction is the ion drive. Pioneered by NASA and other space agencies, ion drives are a new form of electric propulsion. In an ion drive, ions, electrically charged atoms or molecules, are generated by stripping electrons from a gas, typically xenon. These ions are then accelerated to high speeds using electric fields created by electrodes within the engine. As the ions are ejected out of the back of the engine at extremely high velocities, they impart momentum to the spacecraft, propelling it forward. This method is incredibly efficient, but it's very slow. Chemical rockets are still needed for launches to take place. NASA's Dawn spacecraft, which explored the asteroid belt, is a testament to the ion drive's capabilities. But as it stands, ion drives simply can't provide the rapid transit needed for interstellar voyages. They're perfect for long-duration exploration of the solar system, but they fall short in other areas. Nuclear propulsion offers a more powerful alternative. by harnessing the immense energy of nuclear reactions, spacecraft can theoretically achieve much higher speeds than conventional rockets. Nuclear spacecraft propulsion, an advanced concept in space travel, involves harnessing nuclear reactions to propel a spacecraft. There are two primary types, nuclear thermal and nuclear electric propulsion. In nuclear thermal propulsion, a nuclear reactor generates heat by fission, the process of splitting atomic nuclei. This heat is then used to raise the temperature of a propellant gas, such as hydrogen, which expands and is expelled through a nozzle to create thrust. This method potentially offers a much higher thrust-to-weight ratio than conventional chemical rockets, allowing for faster travel to distant celestial bodies. In nuclear electric propulsion, the reactor's heat is used to generate electricity, powering an electrically driven propulsion system, such as an ion drive. This method offers high efficiency and is well suited for long-duration missions, although it generates less immediate thrust than nuclear thermal propulsion. Both approaches leverage the dense energy of nuclear reactions, presenting a potential breakthrough in overcoming the limitations of current space travel technologies, especially for deep space exploration, where high speeds and long mission durations are crucial. However, the use of nuclear materials in space raises significant safety and ethical concerns. There's also the challenge of handling highly enriched fuel, a necessity for such engines. Despite these challenges, the potential of nuclear propulsion remains tantalizing. Russia has announced plans for a nuclear-powered spacecraft, and NASA is exploring nuclear options for future Mars missions. Could nuclear propulsion be the key to interplanetary or even interstellar travel? In our quest for new propulsion methods, we shouldn't overlook the power of the sun. Solar sails, an elegant and fuel-free technology, use the sun's radiation pressure for propulsion. The concept, which sounds straight out of a sci-fi novel, became reality with projects like Light Sail 2. Solar sails harness the power of light for propulsion, offering a unique and efficient means of space travel. A solar sail consists of a large, lightweight, and highly reflective material, often a thin mylar or similar substance. When sunlight hits the sail, the momentum of the photons is transferred to the sail, producing a gentle yet continuous thrust. Unlike conventional propulsion systems that require fuel, solar sails rely solely on the sun's energy, making them ideal for long-duration, deep space missions. The thrust produced by solar sails is minimal compared to traditional rockets, but it accumulates over time, allowing the spacecraft to gradually build up significant speed. This innovative technology opens up new possibilities for exploring the solar system and beyond, as it requires no propellant and can potentially propel spacecraft indefinitely as long as they remain within the sun's influence. Now, let's venture into the realm of the extraordinary. Warp drives. Popularized by Star Trek, warp drives theoretically enable faster-than-light travel by bending space-time around a spacecraft. Until recently, this was purely speculative, but recent studies suggest that warp drives might not be as far-fetched as we thought. Researchers have proposed models that align with Einstein's theory of general relativity. These models suggest that it might be possible to create a bubble of warped space-time around a ship, allowing it to travel at effective speeds greater than light without breaking the laws of physics. NASA has been dabbling in warp drive research, though it's still in its infancy. The main challenge lies in the massive energy requirements and the creation of negative energy, a concept that's still theoretical. Nevertheless, the mere possibility has electrified the scientific community. Are we on the brink of a breakthrough that will open the cosmos to us? In our journey through the possibilities of space travel, we've explored technologies ranging from the controversial EM drive to the awe-inspiring concept of warp drives. While we may not be packing for Alpha Centauri just yet, the advancements and ideas we're discussing today lay the groundwork for a future where such journeys could be a reality. The quest for faster, more efficient space travel is more than a scientific endeavor. It's a testament to human ingenuity and our unquenchable thirst for exploration. If you're fascinated by the future of space exploration and the incredible technologies that could get us there, don't forget to like, share, and subscribe for more content. Share your thoughts in the comments below. Do you think we'll see these technologies in our lifetime?